Okay. The slides, please. Thank you. Good morning, everyone. I'm Nathalie Pauling de la Brouille from LBL, and I have the pleasure to be introducing this session dedicated to the Dark Energy Spectroscopic Instrument, or DESI. DESI is presenting today its first year results, and that's really the focus of this invited session. I first want to thank our sponsors, in particular DOE, who is funding the project, and the 72 participating institutions to this collaboration. DESI is putting today on the archive its results from the first year BAO measurements. There are a series of papers that will be published today. The first 3 key projects are highlighted here, and there will be others coming up. And what you will hear today is a speaker who will present each of these 3 key projects. So the first speaker will be Hee-Jong from Ohio University, and she will present the BAO results from galaxies and quasars out to a redshift of 2. Then the second speaker will be Julien from Berkeley Lab, who will present the BAO results from the Mustapha forest at redshifts above 2. And then the third speaker will be Mustapha Ishak from the University of Texas, Dallas, who will present the cosmological inference of this whole sample of quasars, galaxies, and Mustapha forest across all redshift ranges. So in addition to this presentation, there's a press release that is coming out today, and you also have you will have access at 5 p.m. today to the 3 key projects that you will hear about today, in addition to 7 supporting papers that have been submitted at the same time, and 7 others that had already been submitted and published in the past few weeks and months. So this is all that I wanted to say to introduce this session, and let us thank Hee-Jong, who is coming and presenting the first BAO measurement.
Okay, hi everyone. My name is Hee-Jong from Ohio University. I'm very excited to present the DESI 2024 Baryon acoustic oscillations from galaxies and quasars on behalf of the DESI collaboration. Do I type? Okay. All right, can you go to the next slide, or do I press the next slide? Oh, this one? Okay. Okay, I'd like to thank our sponsors, the participating institutions once again. As the name implies, dark energy, the primary science goal of Dark Energy Spectroscopic Instrument is probing dark energy by measuring the expansion history of the universe. DESI is a dedicated fiber-fed multi-object spectrograph with 5,000 fibers on the focal plane. With 8 square degrees of field of view, the DESI is really optimized for making a large-scale 3-dimensional map of the universe. Okay. The map DESI will make will reach more than the look-back time of 11 billion years. To reach such a large baseline in terms of look-back time as well as distances, DESI will utilize 5 different target classes, and over the course of 5 years of survey time, DESI will take 40 million unique redshifts. For the nearest part of the universe, DESI will use bright galaxy sample, which is followed up by luminous red galaxies, and then the emission line galaxies. And the further away part of the universe would be mapped by QSOs. And the furthest part will be mapped by the Lyman alpha, which will be presented in Julien's talk. This slide shows the survey coverage of the first year DESI data, which we named DESI Data Release 1. Here, the dark brown area is where the survey is complete, and dark blue area is where the survey is only 10 or 20% complete. There is a large variations of the survey completeness, but this is properly accounted for in our analysis. Towards the future DESI data, the entire area will be filled with dark brown. Baryon acoustic oscillations are primordial sound waves that propagated in the very early universe when the universe was hot and dense and photons and baryons were tightly coupled. Imagine an initial fluctuation at any random location of the universe. Because this is a fluctuation in photon, the photon pressure will initiate a spherical sound wave that propagates at the speed close to the speed of the light. As the wave propagates, the universe will expand and cool down. And after 300,000 years after Big Bang, near the epoch of recombination, the universe will become optically thin to Compton scattering, and the baryons will decouple from photons. As the pressure supplying element decouples from baryons, the sound speed suddenly decreases, and this traveling wave suddenly stalls near this epoch. After the recombination, therefore, the baryons and photons are left with the imprint of a spherical peak at the distance that the wave had traveled before the recombination. This is called the sound horizon scale at recombination, and that is the physical size of the BAO feature. The size of the BAO feature is 150 megaparsec. That corresponds to about 200 times the distance between the Milky Way and the Andromeda galaxy. So this is a really large-scale ruler. The BAO imprinted in the distribution of photons are manifested in this oscillatory feature in the power spectrum of the cosmic microwave background data. And after decoupling, baryons can finally see the gravity of the dark matter, and the two fall into the common gravitational well. And not just the BAO, the entire mass, the matter now has the imprint of the baryon acoustic oscillations. The size of the BAO can be precisely measured from the physics that we can infer from the cosmic microwave background data. And therefore, with the known size of the feature, we can actually conduct the standard ruler test. By measuring how small it appears, we can measure the cosmological distances to different look-back time. Our feature is a three-dimensional feature, so we can do the standard ruler test in 3 dimensions. By looking at how small it appears on the sky in terms of the angular extent, we can measure distance called angular diameter distance. And by looking at how small it appears along the line of sight, we can measure Hubble parameters. The two parameters encode the expansion history of the universe and therefore can tell us a lot about dark energy. So let me introduce the BAO scale parameters we measure. First, we measure the azimuthally averaged transverse BAO scale. And if you measure this scale relative to a reference scale based on the fiducial cosmology, we parameterize this as alpha perpendicular. And we can also measure the line of sight BAO scales, which we parameterize as alpha parallel. So equally valid, the other basis is the overall size of the BAO, the spherically averaged overall size of the BAO, which measures the average angular diameter distance to the redshift, and the anisotropy of the BAO, which we parameterize as alpha AP, whether BAO appears oblate and prolate compared to the prediction of the fiducial cosmology. Okay, so BAO is a very large scale feature, 150 megaparsec. It has a distinct signature, spherical peak. As a result, astrophysical or observational effects cannot easily contaminate or mimic the BAO feature. So this is a really robust standard ruler. However, because we are going for the highest precision cosmology test, we care about even small effect. In fact, our ruler is being aging. Ruler has been aged. Our ruler gets blurred and shrinks a little bit during the structural growth, and also due to the peculiar velocity fields. In this cartoon, we start with a clear BAO feature in the very early universe. the inset shows the spherically averaged BAO peak. During the structure growth, the matter will flow toward the nearby overdensity peaks. As a result, in the later time, the BAO peak would appear broadened, and although you cannot see, the location of the peak has been slightly shifted. So that degrades the accuracy and precision of the standard ruler test. Well, good news is that we know how to refurbish our ruler using the method called density field reconstruction. The idea is simple. Because it is the gravitational flow that has degraded the BAO, we just want to reverse it. Based on the observed field, we are going to estimate how much mass would have flowed from the initially almost homogeneous distribution of matter to what is observed today by just simply applying the continuity equation on the observed field and reverse the displacement. So this sharpens the BAO almost back to its original sharpness. And also importantly, this removes the shrinkage of our ruler and gives us the unbiased estimates. So improves the both precision and accuracy, and this became the standard practice for the BAO analysis. Okay, now with all the introduction, let me talk about the DESI 2024 galaxy and quasar BAO. The left panel shows the co-moving number density as a function of redshift for our 4 targets used for this paper, starting with the BGS and LRG in red color, and ELGs. And please note, between 0.8 to 1.1 of the redshift range, the 2 tracers overlap, and we combine the 2 tracers and construct one single combined catalog to analyze the BAO for this redshift bin. And then ELG reaches up to redshift of 1.6, and then the highest redshift is covered by QSOs. In total, we included 5.7 million unique redshifts, which covers the effective survey volume of 18 gigaparsec cube. This is already 3 times bigger than the 2 decades of Sloan Digital Sky Survey BAO analysis. In order to have enough time resolution, we split our 4 tracers into 6 different redshift bins and to probe the expansion history as a function of lookback time. So how is the DESI BAO analysis different from the previous BAO analysis? For sure, it is the biggest data set both in terms of the redshift numbers and also the cosmic volume we covered. And also this is the first time a catalog level blinded BAO analysis, and this was done to mitigate the confirmation bias. To give slight details, using the catalog, we use physical cosmology to map the locations of galaxies in the physical space, and then we use blinded catalogs to bring them back to the blinded coordinates in the observed coordinates. Now, if you use physical cosmology to analyze this blinded catalog, it will map to a different physical coordinates. And we also added additional peculiar velocity contribution blinding to blind the growth rate, and also added the blinding of the primordial non-Gaussianity. So one single blinded catalog is used for several cosmology features. And also, in the DESI analysis, almost all systematics and the baseline methods are determined before unblinding decision. And importantly, for the first time, we used the unified BAO framework pipeline systematic test on all tracers over a wide redshift range, as well as between the 2 conjugate space, Fourier space, and the configuration space, which are typically where we analyze the BAO. And we made physically motivated enhancements to the BAO fitting method. And we used physically motivated a new reconstruction method. And we used a combined tracer to deal with the tracers over the same redshift range. So when could we unblind? First, the base pipeline methods need to be determined with the mock test. And the upper limit of systematics need to be set. We especially was cautious about setting the upper limit so that we do not increase the systematics after unblinding. It was to avoid increasing systematics to dilute any tension between the previous result and the DESI result after seeing the result. So that is a confirmation bias. So we set the upper limit and did not increase the systematic errors after unblinding. The checklist of the unblinding test need to be complete as possible. And also we predetermined what is allowed to change after unblinding. The following are predetermined and allowed to change after unblinding. One is the covariance matrix choice. The simulation-based covariance matrix and analytic covariance matrices, the calibration was still ongoing. And also, without knowing the true clustering, it was hard to determine whether the mock-based covariance matrix is a good match to the unblinded data. So we allowed to make that decision after unblinding. And the analytic covariance matrix was our baseline choice. And if any bug is found in the catalogs, we will of course correct it, but we will correct it without looking at the BAO fits first. And some mock tests for systematics were finalized after unblinding. Okay, let me give you a systematic summary test summary, excuse me. And we concluded that no systematics are detected for the observational systematics and reconstruction choice and the choice of choosing analytic covariance matrix. The rest are assigned with the systematics. The theoretical systematics, meaning the assumptions or priors that went into the fitting method, how much systematics does this contribute? It's about level of 0.1%. And HOD systematics, meaning how much the galaxy BAO is biased relative to true BAO scale. And the fiducial cosmology, meaning what is the impact of assuming the fiducial cosmology in the process of the BAO analysis. Altogether, if you square sum, these two numbers are our final upper limits that we decided before unblinding. These systematic errors are much less than the statistical errors, which means if you combine statistical error with the systematic errors, the maximum effect is only 5% of the statistical error. Okay, finally, are you ready to see the unblinding result? So here I'm showing the highlights of the unblinded clustering statistics. The top panel shows the clustering monopole. And we singled out the BAO by subtracting a smooth component. The top panels, the BAO feature in the top panels tell us this physically averaged over the size of the BAO. The bottom panels are clustering quadrupole, and any feature there really tells us the anisotropy of the BAO when we assume the fiducial cosmology, and points at what is the true cosmology relative to the fiducial cosmology we assumed. The left panel shows the combined tracer, LIG plus ELG, at the effective redshift of 0.93. That is our most precise BAO measurement. And it's measured at the precision of 0.8%. The right panel is showing the emission line galaxies at the redshift of 1.32, and this is the first time high significance BAO detection using the emission line galaxies. Likewise, in the Fourier space, the single peak in the configuration space becomes a series of wiggles in its conjugate space, monopole and quadrupole, the equivalent information. So this plot shows the unblinded galaxy BAO detection level. It shows the chi-squared curves in comparison to the chi-squared curve when we completely exclude the BAO information. The colored horizontal line shows if we exclude the BAO information, really we are getting no scale information, which is exactly what we designed. We want to design the BAO analysis, how we want to design the BAO analysis. For all cases, we have high significance BAO detection. The best case is LRG3 plus ELG1, which is at 9.1 sigma. The worst case is still 4 sigma detection with the BGS. You are probably looking at ELG1, 3.3 sigma, but that is combined with LRGs as a combined tracer. So the lowest significance is 4 sigma from BGS. If you combine all the measurements, the aggregate distance precision with year 1 data alone is 0.52%. In comparison, all the SDSS Galaxy BAOs over 2 decades gave us 0.64%. So with the first data alone, we are doing 1.2 times better than all the previous BAO measurements for the Galaxy BAOs. This shows the consistency test we have conducted with the unblinded data. The top rows, the top whiskers show the baseline, our default measurements. The second rows show the pre-reconstruction BAO measurements. We have bigger error bars, just showing the improvement due to the reconstruction. And the rest of them show the result when we introduce a slight perturbation around our optimal choice of the pipeline. So you see all the measurements are fairly consistent, very consistent with our baseline measurement, showing our analysis is stable against small perturbations around our optimal baseline choice. All right, here I'm showing the BAO Hubble diagram. The left panel is based on the overall size of the BAO. It's telling us the spherically averaged distance scale to various the redshifts. The colored points are, of course, the DESI data points, and the dashed line show the Planck lambda CDM best fit, and the solid line shows the DESI lambda CDM best fit that Mustapha will talk about. The highest BAO measurement, our most ancient BAO measurement, will be presented by Julien. By looking at it, you probably notice that we tend to agree with the Planck prediction just visually, while we are pointing at smaller distance scales for redshift less than 0.8. The right panel shows anisotropy of the BAO in comparison to the Planck, the lambda CDM. So now let me divide all those lines by the Planck, renormalize all the measurements with the Planck lambda CDM best fit prediction, and add the previous, the BAO measurements. All the gray points are the previous BAO measurements in comparison to the DESI. In the top row, above unity means a bigger BAO size, and below unity means the other way around. Below unity means a bigger BAO size. Above unity means a smaller BAO size. So this shows that we tend to observe bigger BAO scale compared to the prediction of the Planck and compared to the previous BAO measurement. Okay, another way to look at it, the transverse BAO and the line of sight BAO. Okay, so some of you who are very observant probably noticed some seemingly tension between the SDSS and DESI. So this is a redshift of 0.7. So in order to see whether the two measurements agree or are discrepant, we have to consider the cross-correlation between the two measurements. They have some shared sources and shared volume. The cross-correlation between the two are 0.2, theoretically. However, because they went through the different pipeline, the cross correlation is probably less than 0.2. 0.2 is the optimal case. So we derive a 2.723 sigma discrepancy between SDSS and DESI at this redshift, depending on the assumption of the correlation. To our best knowledge, we conclude the difference is consistent with statistical fluctuations. So with the future data, we will observe whether this discrepancy goes away or remains. However, I'd like to emphasize the value of the blinded analysis. There has been no effort trying to align the DESI measurement with the previous BA measurements because our measurement has been completely blinded. So this is just what we get. So given all the improvements we made in the DESI pipeline, we wanted to quantify the difference in terms of the BAO measurements. So we picked the 3 redshift bins from the Sloan Digital Sky Survey, the published results, and reanalyzed using DESI pipelines. In this plot, the red data point shows the EBOS both published, and yellow shows when we use the clustering measurements of BOS and EBOS, but use the DESI feeding pipeline. And the blue shows when we put the catalog from EBOS and EBOS all the way through the DESI pipeline. There's slight differences. After checking the differences, we concluded that the reanalysis of Sloan is SDSS is consistent with the SDSS published because they are going through different pipelines. If you use the DESI reanalysis of the Sloan to measure the discrepancy between the SDSS measurement and the DESI measurement, we find that the discrepancy, the tension slightly decreases to 2.5 to 2.7. Okay, so before concluding, I'd like to emphasize that all the work presented in this talk, as well as in our alphabetical paper, is really the culmination of all the supporting task efforts that are listed below. All the interesting part of the results, the practical part of the results are really presented in these papers. 5 of them are already in public today, and the rest of them will come out very soon. To conclude, we have made the most precise galaxy BAO measurements with only the first year of the DESI data. The aggregate precision is 0.52%. This is one of the first blinded analysis, and it's the first catalog level blinded BAO analysis. We have used unified BAO analysis for all tracers over a wide redshift range, both Fourier space and in configuration space. And we have made the highest precision galaxy BAO measurement for redshift greater than 0.2. And we also have made the first significant BAO detection using the emission line galaxies. The final DESI data will be about 3 times larger data set than the DR1. Okay, thank you.
Thank you, Hee-Jong. Are there any questions for Hee-Jong in the room?
I have a question here.
Yes, please.
Maybe someone else will respond to that in other talks, but could you quantify the discrepancy with the Planck data at low Z?
That would be in Mustapha's talk.
Yeah, all the cosmological inference will be in the 3rd talk. And so here we're presenting the data first, low redshift, and then high redshift, and the cosmology inference will come in the 3rd talk. Other questions from the room? Yes, please.
I'm just curious about how long it's been since you unblinded.
We unblinded in December during our collaboration meeting in real time.
Must have been very exciting.
Oh yeah, it was exciting.
Any other questions? Okay, I guess you're all excited to look at what is coming up in the next few talks. Thank you, Hee-Jong, very much for this presentation of the low redshift up to redshift of 2 results from the DESI survey. We will now continue with Julien from Berkeley, who will present the Lyman alpha results, and therefore the BAO measurement that we've done with DESI, again with the first-year data set, but using the Lyman alpha forest that is observed in quasar spectra. Julien, take it away.
Okay, so I'm very, very pleased to be here and present those results. So this is the Lyman alpha results. So I'm Julien from LBL. I worked with Andreu Fontribera and Alma Gonzalez Morales as coordinator of a working group, but got a lot of help from a lot of people, including Andreu Cucheu, Cesar Ramirez Perez, Callum Gordon, Hiram Alcantara, Alison Brotzeller, Paul Martini, Jim Rich, and others. So this is just the analysis of Lyman alpha that I'm going to present. But of course, it's been 10 years since we've started this program. We built the instrument, we installed it, we commissioned it, we observe every night, and we have a data team that is processing all of this data every day, and we're talking about millions and millions of spectra. So thanks to all of our sponsors. So I'm talking about the highest redshift. So Hee-Jong has made a fantastic introduction to our BAO measurement. So I'm talking about the Lyman alpha forest at a redshift above 2. That's typically 11 billion a year away from us. So it's interesting, this probe is very interesting because it covers a very wide redshift between redshift 2 and 4. It extends the lever arm and to unleash degeneracies among cosmological parameters. So you have one example here. It's actually from the EBOS collaboration that the contours between omega matter and H0, considering either BAO at redshift lower than 1 in red or higher than 1 in gray, and combined with Big Bang nucleosynthesis. And it's only when you combine those 2 probes that you can get a very sharp measurement of H0 and then see this disagreement we have today with a distance ladder. So it's also really probing distances in the matter-dominated era. At that time, the contribution of dark energy, if it's a cosmological constant, is actually very small. So it's interesting to look at that. So what is the Lyman alpha forest? So I grabbed here some nice plots from Andrew Ponson that you can find on internet, and there are very nice YouTube animations about that. So imaging to the left the emission of a quasar, which is really a supermassive black hole, where you have a lot of emission in the UV. So here you have in particular this Lyman alpha, broad Lyman alpha emission at 1200 angstrom. And then the light goes through the universe towards us. And as it goes through, the quasar light is being redshifted because the universe expands. But at the same time, you get more absorption at the Lyman alpha line. So now it's in absorption. And you build this forest of lines that we call the Lyman alpha forest. From time to time, the line of sight crosses the outskirts of a galaxy, and you can have much more absorption, and you get what we call a damp Lyman alpha system. And also, you start detecting other elements like carbon and silicon. So what we are doing here is using that to probe cosmology. So this transmitted flux fraction F, it's a cosmological probe of the fluctuation of neutral hydrogen density in the universe. It goes as e to the minus an optical depth, which is proportional to the neutral hydrogen. So it works because actually the universe is mostly ionized, and the neutral fraction is only about 10 to the minus 5 after reionization. So this gives us optical depths that are typically below 1. So it's exactly what we need to use that as a probe of cosmology. So on the right-hand side, you have a plot of these optical depths between redshift 2 and 4 with different measurements, including one from DESI that will be published very soon. And you see that it's typically of order of 1. So this is our observables. Absorption in the quasar of spectra, and you have in the spectra of quasars, and you have an example here of a quasar at a redshift 3.6 on the bottom plot. And this forest of lines is probing the neutral hydrogen between redshift 3 and 3.5 for this particular quasar. And now we have hundreds of thousands of them, and combining all of that, we probe the intergalactic medium between redshift 2 and 4. So what we do actually is very similar to what Hee-Jong has shown. We're doing a correlation function. So we build from this data a transmitted flux fraction contrast, a delta, and then we correlate those delta as a function of separation. So just like Hee-Jong has shown, we have a longitudinal separation and transverse separation from redshifts and angles, and they are converted into separations with the fiducial cosmology. So we measure the Lyman alpha autocorrelation, so really correlating those absorptions in different lines of sight, but we also measure the Lyman alpha quasar cross-correlation, because the quasar itself is, of course, a probe also of matter. And it's interesting, in fact, that those two observables have about the same statistical power, because there's a unique quasar, but it has a much stronger bias. It's a much stronger probe of a large-scale structure. So when we make those measurements as a function of separation, we get the kind of plots you see on the bottom. Those are correlation functions as a function of separation in units of H inverse megaparsec. And the y-axis is a correlation function multiplied by r square, actually, to enhance the signal at those scales. The correlation for the Lyman alpha quasar is inverted because a quasar has a positive bias, where it has an absorption in Lyman alpha has a negative bias. So the product of the two gives you this inversion. But it's exactly the same thing. Last introduction plot slide is this one. I want to highlight the fact that this correlation is actually very asymmetric. So Hee-Jong has really presented, again, this kind of plot where you see the signal as a function of r perpendicular and r longitudinal. And in the case of the Lyman alpha forest, you have a very strong redshift effect, and the correlation function is very negative along the line of sight. And you see also strange bumps along the line of sight at small value of r perp. Those are caused by other absorptions, other transitions in the Lyman alpha forest. I will come back to that later. So on the right-hand side, you see our measurement from DESI in 4 what we call wedges, which are 4 regions of this 2D space where we average as a function of this mu parameter. Okay, so now I'm going to present the DESI year 1 result. You have the footprint on the graph. So the blue is a complete footprint that we will achieve at the end of our survey. The green dots are all the pointings that we have done after 1 year with DESI. And in red, for comparison, is a footprint of SDSS. So today, we have more than 700,000 quasar tracers at a redshift greater than 1.77. Those are the quasars that we use in the cross-correlation. And we have more than 400,000 Lyman alpha quasars at redshift greater than 2. This is twice as large as the full SDSS sample, but we haven't yet observed them, all of them at full depths. You see on the right-hand side that for almost half of them, we have observed them only once, when we want to observe them 4 times by the end of the survey. In terms of redshift, this is the histogram of the quasar redshift in orange for DESI compared with SDSS in green, and the histogram of the absorption features in the Lyman alpha forest. On the right-hand side, you see the redshift of pairs that we are using for our correlation functions. So our effective redshift is 2.33, and most of our signal is between redshift 2 and redshift 3. What we are actually measuring are 4 different correlation functions based on 2 spectral regions. So it's actually kind of a complex data set. We do Lyman alpha autocorrelation from the Lyman alpha forest itself, which is region A on that plot. We do also the autocorrelation of Lyman alpha, but looking at two different regions of the rest frame of the quasar. This is Lyman alpha A cross Lyman alpha B. And then we cross-correlate those two regions with the presence of a quasar. Those are those four correlation functions presented as a function of separation and in different wedges. So the BO peak appears at a scale of about 100 H inverse megaparsec. So you can see it in almost all the plots. It's very strong in the Lyman alpha autocorrelation on the upper left plot, which is in the A region, and also in cross-correlation with quasar on the upper right plot. So now I want to just give just a few details about what we are measuring, without going too much in details. First, the estimator of the correlations that we have are kind of straightforward. They are simple weighted average of those products of deltas with weights that are optimized, of course. They combine measurement errors and also the known variance, physical variance caused by large-scale structure with prefactors that are optimized for the measurement we're doing, especially that the prefactor is a function of redshift that accounts for the evolution of the bias of the tracer with redshift and also the growth of structure. On the right-hand side, you have a similar estimator for the quasar Lyman alpha cross-correlation. Our full data set is really large. It's more than 15,000 data points. And we have found that we really needed to account for the full correlation of the sample, in particular the cross-covariance between the four correlation functions that I presented earlier. So this was not done in the past. So this accounts for about 10% of the uncertainty, and it has to be accounted for. So we measure our covariance by doing subsamples on the sky with patches of about 250 by 250 megaparsec divided by h. And we have a smoothing scheme that has been validated on MOX and also an analytical covariance. On that plot, you see this crazy correlation matrix, but look at the scale, it's only plus minus 0.01. So in fact, we detect a correlation, but it's a faint correlation. Another technical aspect is those contaminants to the Lyman alpha forest I alluded about earlier. So first, we have silicon lines that are really in there, in the forest. And when you measure an absorption at a given wavelength, it's either Lyman alpha or either one of those. And if it's one of those, then you're making a mistake in converting wavelengths to redshift. And because of that mistake you're doing, you get extra correlation along the line of sight. We have also other absorbents that are contaminating the forest at much lower redshift. So you see them only with their autocorrelation, but you have to account for them at some level. And then finally, we have noise that is induced by the data processing. We are correlating our spectra when we are calibrating them, and we have to account for that as well. So this has been this is presented in a companion paper. And then final technical point about the BAO, so really simplifying what we are doing. So we have a complete model of the correlation function. It has 17 free parameters. We are interested about only two of them, which are the alphas. Those are the parameters that stretch the peak component of the correlation function to measure the BAO. So what we do is exactly similar to what Hee-Jong has presented. We separate a smooth component from a peak component, and we only stretch as a function with a peak component. And we marginalize over the other 15 parameters. Right, now I think I want to really highlight the process, which has been to conduct a blinded analysis from end to end. So that it means that we develop the analysis on a mock dataset, synthetic dataset, and blinded data. We decided in advance on a list of validation tests before unblinding, And then we made a report to the collaboration once we were happy with all those tests. And then we unblinded in December, as Hee-Jong has said. So our blinding method is actually very simple. The one we picked, it's different from the one done for galaxies. We decided to simply add a perturbation to all of the correlation functions we measure. And that perturbation is tailored to produce a shift in the BAO peak. And that shift is actually been modeled out of the best fit Lama alpha forest model from the SDSS survey. So we had already in advance a known good model for the Lama alpha forest. Then this is a list of tests that we decided to do before unblinding. So we wanted first to use a synthetic data set to demonstrate we recover an unbiased BAO parameter with a threshold that we define in advance to be less than 1/3 of the final statistical uncertainty. And we also wanted to demonstrate we have a good understanding of the statistical uncertainties on the BAO, the scatter. And we also did a lot of data splits on the blinded data, comparing Lama alpha autocorrelation and Lama alpha quasar cross correlation, the different wavelength regions, different sky regions corresponding to different target selection, different signal to noise of quasars, and different shape of quasar spectra. And then we wanted to validate that our analysis was robust to many, many different choices we made. So I'm just going to flash some of those results. First about MOX. So we use 10 gigaparsec cube boxes of what we call log normal MOX, which are in fact simplified simulations based on FFTs of Gaussian random field, but with a realistic survey footprint, realistic exposure time, realistic noise and resolution from an actual instrument simulation, because we're looking at spectra here, it's important. We have 100 of those 100 simulation of the full DESI survey of the 1-year sample with one set of MOX, and another 50 obtained with a different code again to test for potential systematic effects. On the right-hand side, you see a comparison of the stacks of the 100 simulation. Those are the dots, compared to the curve, which is the best fit model. So you see by eye that we have the good model on all scales and for all correlations. But now the real validation is to perform the fit on this MOC data set and see what we get. From the stack, we get a result that are consistent with the truth within 0.4%, with actually statistical uncertainty from the MOCs themselves. And in any case, this is smaller than our threshold of 1/3 of statistical error of DESI, which is shown here as a dashed curve. The colors are the different set of MOCs, so there's also maybe some uncertainty in the MOC production themselves. So we passed this test. Second test, it was looking at the scatter from MOC to MOC. It's shown on the left as a function of alpha perpendicular and alpha parallel. And we looked at the RMS of the deviation from the truth divided by the expected uncertainty that we get from our covariance. And we find that those pool distributions are consistent with 1. Then about data splits. So we didn't do random data splits. We really wanted to have them limited and with a physics question for each of them, basically. So going from top left to bottom right, we splitted our sample between low and high signal-to-noise quasars. This is a test of the spectroscopic data reduction, and we found that the results were consistent. Right-hand side, different kind of quasar spectra depending on the strength of the carbon-4 emission line. This is a test of how well we we divide the continuum of the quasar, and also if there is any bias-associated issue there, and we don't see any effect. On the bottom left, it's north versus south. We use really 2 different sets of telescopes to target, to make the imaging that was used to select the quasars. And so it was important to check that we were getting the same results in those two regions, and that's the case. And then we looked at different spectral regions, A and B, which have different noise properties, different continuum, and different kind of contaminants. And we also find that they agree. Then we look at all the tiny little parameters that we have in our analysis. I will not go through all of them, but the message is that if you look at the purple, the green, the orange, and the blue, they are all within the gray band, which is 1/3 of the statistical uncertainty. The red dots have a little bit more excursion because it corresponds to variations where you change a little bit the data set, and so you have some extra statistical noise because of this variation in the data set. We verified that they were statistically consistent. And the very last test we did is to add some completely empirical parameters to our correlation function to get the very best fit we can imagine of the full correlation function. So those are polynomial terms that we add, and they change the BAO by only 0.1%. So we are not sensitive to the actual details of the shape of the correlation function. So using all of that, we decided to unblind our result, and this is shown here. So this is the contours on the alphas. The alphas are, again, the stretch parameters with respect to fiducial cosmology. The fiducial cosmology was chosen to be the best fit lambda CDM from Planck, 2018. You have the numbers here. And when we unblinded, we moved almost by 10% in alpha perpendicular. So we worked for months with alpha values that were really off, so we were a little bit worried. But when we unblinded, it turned out to be consistent with Planck lambda CDM. And you have the numbers. Precision is about 2% along the line of sight and 2.4% transverse to the line of sight. So when you then you can interpret those alphas as a measurement of the ratio of the Hubble distance to the sound horizon and the angular diameter distance to the sound horizon compared to the fiducial cosmology, and then you have the result from the fiducial cosmology, so you get your actual physical measurement. It's given here. It has a correlation coefficient of minus 0.5, so it's kind of correlated. The best combination of those two numbers gives us a precision of 1.1% at a redshift of 2.3. So this is the best ever measurement at that high redshift. On the right-hand side, you see the contours where we have separated Lyman alpha autocorrelation and Lyman alpha quasar cross-correlation. It's the first time I'm showing that. They agree very, very well. And I think it's a very impressive test because if you think about it, a quasar is really the presence of a supermassive black hole in a galaxy, an AGN somewhere in the sky, whereas Lyman alpha is a tiny absorption feature that you detect in that spectrum. It's kind of spectacular that we get exactly the same answer with those two data sets. Then we combine our result with SDSS, which is really the previous measurement. So we didn't fully redo the analysis. We could have done that, but we decided just to make the minimal work for the comparison because we know that we are getting much better data in the next 3 years. So we estimated just the covariance between the two data sets by looking at subsamples in the sky, and we found out that this covariance was only about 10%. But we have a full covariance matrix that you can find in the paper, and that improves a little bit the measurement, and now we get a 0.9% isotropic measurement. So there are supporting papers to this analysis that are listed here and that you will find on the web tonight. So in conclusion, after just 1 year of operation, DESI have observed more than 400,000 quasars at redshift greater than 2. It's twice as many as all of SDSS. We have the most precise measurement to date of BAO between redshift 2 and 4 from the combined measurement of the Lyman alpha autocorrelation function and Lyman alpha quasar cross-correlation function. The analysis has been developed on a fully blinded data set. The isotropic BO scale precision is 1.1%, and the results are consistent with SDSS. And now it's Mustapha who's going to explain to us how we can use that to do cosmology. Thanks.
So are there questions for Julien on this measurement of the Lyman alpha forest and how we extract BAO from those data? Yes, please, if you want to walk to the mic.
Hi. So you focused mostly on Lyman alpha, but damped Lyman alpha absorbers are also interesting in their own right. Are there any plans with DESI year 1 to do DLA cross correlations or make a DLA catalog and release that? Anything of that nature?
So actually we have, I didn't speak about that. We have a full DLA catalog, and we're actually using it to mask out the DLAs because we found out that this improves our measurement to mask them out. So we have a threshold to mask them in our data, but yes, of course, they are themselves tracers and we can use them as well. We haven't done that for this so far, but clearly it's something we want to do.
Thanks.
Other questions for Julien? Okay, if not, let's thank Julien again. And we'll continue with the third talk with Mustapha Ishak, who will present us the cosmological inference from the whole data set of DESI. Just before Mustapha starts, I just want to highlight that the three speakers you have here presenting today played major roles in the collaboration. DESI is a huge collaboration. It's almost 1,000 people, with about a third of them being grad students from all over the world. The 72 institutions covered all the continents. And so it's quite an endeavor to get all these people working together and coming up with the results that are presented today. And we have, of course, people who are taking a lot of responsibilities in the collaboration, and in particular, the three speakers you have here today, each played a role by supervising one of these working groups or key project activities, and they led that analysis so that this whole large collaboration can produce the results that you're seeing today. So a big thank to these speakers and all the people who have been working with them in DESI for the past years to get these results. Go ahead, Mustapha.
Thank you. Well, hello everyone. My name is Mustapha Ishak from the University of Texas at Dallas, and I'm very delighted to present to you today the results from the first year of DESI, the cosmology results, and that is on behalf of the entire DESI collaboration. First of all, a big thanks to all our sponsors that you can see there on the logo. All the sponsors made this journey happen, made this journey of DESI happen. So a big thanks to them. And a big thanks also to all the 72 institutions of DESI who worked very hard to make this possible. Now, what is DESI telling us about the universe, about the cosmological parameters? First, let's recall that DESI is an experiment that was designed and built with the chief objective, with the chief goal, to constrain the nature of dark energy that is causing the acceleration of the expansion of the universe. And it delivered. It delivered to us a precise measurement of the expansion history of the universe for the last 11 billion years. If you think about it, the age of the universe is 13.8 billion years. And DESI is able to give us the expansion history with precision for the last 11 billion years. In doing so, DESI is able to put tight constraints on the properties of the dark energy, on its parameters. DESI is also able to give us information, constraints, about the curvature, spatial curvature in the universe. And DESI is able also to give us constraints about the neutrino masses in the universe. Let's back up 1 second here. And what is dark energy? Dark energy is a component in the universe that dominates the budget, the energy budget in the universe, with roughly 70%, nearly 70%. And this dark energy goes into the Einstein equations, like a fluid, like a cosmic fluid. A cosmic fluid with the negative equation of state. And that negative equation of state, the equation of state is the pressure over the energy density times c squared. The fact that it is negative, the equation of state, that it is negative, and the fact it's negative and smaller than minus 1/3. So because of that fact, when it is put into the Einstein equations, when it is put into the Friedmann equations, it does cause the expansion of the universe to accelerate. So mathematically, the acceleration of the universe is not a problem. However, what we don't know is the physical nature of dark energy. There are several candidates that have been proposed since the discovery of the cosmic acceleration in 1998. And those candidates, they have the equation of state that goes around -1, but it allows for some departures from it. And it is, DESI can measure the equation of state with a high precision. And in doing so, it can discriminate between the different candidates of dark energy. How does it do it? I will not show you many equations. I will show you this one. So my colleagues gave 2 talks before me, and they talked about these distances, dm over rd, the sound horizon, hd over rd, and dv over rd. These distances depend closely on h of z, the function for the expansion history of the universe. And if you can look with me here, if you can look, you see that in this term here, so it constrains omega m, it constrains omega k, but it constrains this omega dark energy and also the equation of state of dark energy here, W0, W1, or WA. So that DESI goes after those ones and it constrains them. And in fact, it does it very well. It does it very well for the following reason. You have seen this plot before. The important point here is that DESI goes after different tracers, and those different tracers, they constrain the expansion history at different red shifts. It's different redshifts, and that has a big plus, as we will see. We will see it immediately on this figure. So if you look with me at this figure, what you see that different tracers, the 7 tracers we talked about them, they constrain this omega m and H0 RD. This is within the standard model of cosmology, the lambda CDM, made of a cosmological constant, the dark matter, and the baryonic matter, and no spatial curvature. So within this model, you see you have different contour plots. And if you look at them, they don't have all the same direction of degeneracy. It goes slightly up from one tracer to the other. This is a very important point. Why? Because it allows, we can see they are consistent, they overlap. But we can see also what it does. It allows to break the degeneracies between these constraints. And when we put them all together, you see here, look at the center. There is a dark black contour here that is the resultant of all of these. That goes a tiny contour plot here that gives us the constraint on omega m and gives us constraint on H0 RD. In fact, just DESI alone constrained to 5% omega m and constrained to nearly 1% H0 RD. We can even contemplate this on this plot here. If you look at this plot, we see that in blue is DESI, the constraint from DESI. And this is only 1 year of DESI data in blue. But if you look at the orange one here, this is, as was said in the previous talk, this is 2 decades from SDSS. And we see that, in fact, DESI already matches that, and in fact, it does better. The message to take also is that the DESI result is consistent with the one from SDSS and the one from the CMB. And by the way, when I talk here in this talk, when I talk about the CMB, it means we are combining Planck temperature and polarization plus Planck and ACT lensing, CMB lensing. That's what I will call CMB unless I specify otherwise. And now we got to the Hubble constant, or what DESI is telling us about the Hubble constant and the Hubble tension. In fact, it has been only 100 years that we have been debating about this constant. If we take DESI result and we combine DESI BAO with only a constraint from the Big Bang nucleosynthesis on omega B, the physical density of the baryonic matter. If we combine just these two, it is good enough to break the degeneracy between H0 and RD. It breaks this product and it sets H0 free. It sets H0 free so we can measure it. And we did. H0 we find, and I won't be reading for you a lot of numbers. Let's read this one. So it's 68.53 plus or minus 0.80 kilometer per second per megaparsec. This is nearly a 1% measurement of H0. And in fact, this is in 3.4 sigma tension with the shoes measurement from the collaboration, the shoes collaboration measurement using the local distance ladder. And this is no CMB here, okay? This is no CMB. This is just combining DESI and BBN. And we get this result here. Let's have a look on a bigger plot. Let's have a look together at that. So if you see here, and here is the picture, is that the CMB data is here. So it constrained at some 67 kilometer per second per megaparsec. And we see DESI here, this is the result we just talked about, sits between 68 and 69 right here. Also, we combine DESI with other priors and other small data sets, and it sits here. And the measurement from the shoes collaboration is somewhere here, a little bit at higher values, So DESI has its word to say about H0. We move on now to cosmic curvature. And when we look at cosmic curvature, so DESI in blue combined with the data from CMB in purple here, the takeaway from this slide is that if you look at the purple ellipse confidence contour, if you look at the confidence contour, so it is shrinked by a factor of 5, by adding DESI. And that reflects in a factor of 3 when we look at the constraint on omega k here. In fact, this is a very tight constraint on the cosmic curvature, and again in favor of spatially flat universe. Here comes the dark energy story, the dark energy journey. We start with the model that is called WCDM, and what we did here, we take the lambda CDM standard model with a cosmological constant of -1, but now we allow for this W to change from its minus value. It's still constant in time, but it can take different values than -1. We call it the WCDM model. And if we look at that, here comes a plot. So we look at that. One remark to make is that you look, the constraint on from DESI comes, they are in blue, in the blue contour, and so is practically vertical. If you look, the CMB is this purple that goes in diagonal, and then the supernovae data, they tend to go kind of from right to left, and here. And in this work, then when we combine from external data sets. We use the supernovae. We had 3 supernova data sets that we used. We never combined them. We used them separately, one at a time. So we have the data from Union. We have Union 3. We have the data from the Pantheon Plus, and the data from DES year 5 supernovae. The point to take from here is the little orange contour plot here at the center. And that contour plot in the center, it tells you when we combine these 3, how we can shrink and constrain the equation of state. It's also that DESI is consistent with the cosmological constant. Let's look at the numbers. Here they are. Here are the numbers, and if we combine, for DESI only, we get this one, about 15% errors, uncertainty, and then, but it sits on a -1 for a cosmological constant. If we combine the 3 data sets, it sits on again, very close to -1 with 2.5%. This is consistent with lambda CDM, with a cosmological constant, but there is a big however here. If we allow for the equation of state to change in time as it should, if we allow for that, and we use here this CPL parameterization that is widely used in the scientific community, here what we get. We look in blue. Let me look with you through this, guide you through this plot here. We look in blue. This is DESI contour plot, constraint from DESI. And we see that while the majority of the contour plot is in this quadrant here, however, we see, please pay attention and look, there is a horizontal line of 0 and a vertical line of -1. Those are for the cosmological constant, -1 and 0. And we see that in here, this is consistent with, in the second contour here, the point here that I'm pointing falls into the second contour of DESI here. However, when we take DESI data, and we combine it with the CMB, we observe a trend. We obtain a 2.6 sigma discordance with the value of the cosmological constant. So you see this orange plot here, this orange contour, and you see it. You see that the point of a cosmological constant here, the point right here, is not inside the ellipses. So this is an interesting trend. And in fact, I will tell you an anecdote about this. When we were on a DESI collaboration meeting in December, in fact, exactly on December 12th, on the December 12th, our colleagues and from DESI, we unblinded the BAO results. And we went back to our hotel rooms. And a bunch of us spent that night from the 12th of December to the 13th of December, spent that night using the data, seeing what the data is telling us. And I can't say it better. One of my colleagues, on Slack channel, we were some in US, some in Europe, some all over the world. And one of our colleagues said, oh, we are like kids in a toy store. And I can't say it better. That's exactly how it felt. So we can continue the journey. We can continue the results. And here we do the same thing. We take our DESI BAO year 1 data and we combine it with the supernova data one at a time. So you see that again, if we combine DESI with Union 3 here in orange, or we combine DESI with DES year 5 supernova here in blue, we see that those two combinations also are away from the vertical line here, -1, and the horizontal line of 0. They are away from it also. In fact, we see this trend of the data, the contours laying in this fourth quadrant. 1, 2, 3, 4, fourth quadrant. And this fourth quadrant here, we see that the DESI plus Pantheon here is shyly sympathetic to the lambda CDM. And in fact, as I said before, it's really fun to sit in front of our Jupyter notebooks and hit the button, and we take a big breath to hit the button and to see, in fact, what the universe is going to tell us. And the universe did not disappoint. We see that we obtain, when we combine the data, the DESI BAO plus the CMB plus Pantheon plus, or DESI BAO plus CMB plus Union 3, or DESI BAO plus CMB plus DES 5 supernovae, when we combine these, each combination has moved away from the -1, 0 value of a cosmological constant. So there is this again, so you see the quadrant represent a value of W0 that is greater than -1 and smaller than 0, which are the values for the cosmological constant. The first logical question that comes to mind is, what is the significance? What is the significance of this result? And we did that. We looked at the significance of this result. And what we found is, so for the first combination there, it's 2.5 sigma. and for the second is 3.5 sigma, and then for the third is 3.9 sigma. And don't forget, also just DESI plus the CMB gives us a 2.6 sigma. Well, another logical thing to do with this result, when we obtain another logical thing to do, is to look into a Bayesian model analysis, a Bayesian model selection analysis to see, and we did that as well. And the results are consistent. The results are consistent with the picture above that you see about the departure from the -1, 0. And now we can reflect a little bit on this result. When you look at this result, so are we seeing first hints of a time-varying equation of state of dark energy in some tension with the cosmological constant of a lambda CDM? But again, we need to be prudent with these first results. We need to be prudent with these first results, and we are digging further into them with further data from DESI. However, if this persists and this grows in its significance, this is an interesting result. This is very interesting results. And in fact, for some people who have been working for 2 decades on the cosmological on the cosmic acceleration and so forth, the question that comes to mind is, but again, we have to be prudent, is nature, is the universe giving us a break about the cosmic acceleration problem? But again, we have to be prudent and wait and see how this persists, how this grows, and look at it. Okay, so now we have, next we have the DESI is also, and again, this is an important point that I mentioned earlier quickly, but I will again say it again. So DESI brings tight constraint on the cosmological parameters that we showed earlier. And when you combine DESI with other probes, it breaks degeneracies, and it does it well. It breaks, in this case, degeneracies with the CMB, and it provides us with constraint on the neutrinos. Excuse me. And it gives us, in fact, here, better constraint than the previous ones. Excuse me. And this is within the lambda CDM model, But of course, since we are seeing also the W0 WA CDM we considered it, so we also see that as soon as we assume a different background, then the bound on the neutrinos is diluted. And you can see that on this plot here. So you can see that on this number here. So the takeaway here is that DESI does well, but this result is model dependent and also prior dependent. All right, we arrived to our summary. Excuse me. So here is our summary. 1, when you take DESI plus BBN, the Big Bang nucleosynthesis, it constrains H0 to a 1% precision. It constrains it to 1% precision, and it gives us a 3.4 sigma tension with the results from the Schu's collaboration from local measurements. That is 1. 2, when we combine DESI and CMB, it gives us a very tight, one of the tightest constraints on the cosmic curvature. It gives us, and it's indicating a spatially flat universe. Now, when we go to the dark energy, again, the heart of our talk, the heart of our results, when we go to the dark energy, if we consider a model with a constant equation of state, we assume that, we want it to be that way, then the result that comes out of it is consistent with -1 of a cosmological constant. However, when we assume that, when we give the freedom for the equation of state as it should to vary in time, then we find that DESI, data, DESI BAO, plus the CMB already gives a 2.6 sigma discordance with the cosmological constant. And if we combine DESI with one of the supernova sets like Union 3 or the DES year 5 supernovae, that also gives some preference, some trend to this quadrant. How about maybe we coin it today the preferred quadrant of dark energy? We move on then next to do the following things, is to consider DESI plus the CMB plus one supernova set at a time in this order. So Pantheon plus Union 3 DES year 5 supernovae. If we do that, then the preference for this quadrant is increased, and some hints of a departure of the -1, 0 value of a cosmological constant, those hints indicate some tension at the level of 2.5 sigma, or 3.5 sigma, or 3.9 sigma with the cosmological constant. So again, I would like to say, this is very interesting result, but we need to look at it prudently, and we are digging more into it using more data from DESI. But if this persists, and it grows in significance, this is a very interesting result. And maybe we are looking at some break on the cosmic acceleration problem. And finally, we have seen that DESI BAO breaks degeneracies, and when combined with the CMB, gives us improved constraints on neutrino masses. So this is what DESI is telling us today about our universe. This is what DESI is telling us today about dark energy. Thank you all for your attention.
Thank you, Mustapha. Are there questions in the room? Yes, please go ahead.
Hi, thanks for that fascinating talk. I was wondering, your use of the CMB data, you were careful to define exactly what you meant by CMB. And there are also, you're using the 2018 for the, everything except for the lensing, the CMB. And there's been some analyses using the same maps that were used for the, I guess the PR4 maps in Planck that you used for the lensing. And there's been some analyses using those maps that resolve some strange things that were present in the initial Planck analyses with a lens and the curvature constraint there. And I'm wondering how robust your results are to, I know you're still getting really interesting things even without the CMB data, but I'm wondering, have you looked at, if you use the Tristam et al., for example,
That's a good question, and the answer is yes. Yes, we did. If you look in appendix, yes, we did compare the result between PR4 and PR3, and we found no changes, so there is consistency. And by the way, there is consistency, and it's all consistent. And by the way, your question remind me to tell that our papers, I think Nathalie said already, our paper, cosmology paper, should appear today on the archive, and you will see an appendix there about it. So the answer is yes.
Thank you.
Great question, yeah.
And the papers are already available on the DESI webpage. If you go on the public page, there's, no, it's not on the public, on data.desi.lbl.gov, I believe. That's where we have the PDFs of the papers that are already available. And otherwise, you wait till 5 p.m. today, and they will appear on the archive as well. Yes, please.
I think.
Oh, okay, sorry. Yes, Rocky, go ahead.
Yeah, thanks. Very exciting results that you presented. It's going to take a while to digest them. In the first tranche of papers coming out, are you going to say anything about parity violation?
We did not.
Okay.
Not, yeah.
Yeah.
But there's a group working on that. So yes, that activity is clearly ongoing. It is not in the set of papers that have been submitted so far, basically because we kept the data blinded for so long that nobody had access to the unblinded data to finalize these complex analysis. But this is work in progress, and you will see results, hopefully with this first year data already in the next few months.
All right.
Yes, go ahead.
Mustapha, can you make a comment about the discrepancy with Planck at low Z, one of these various first slides that we saw?
Okay, you're referring to, there is, when we compare the CMB and any result from the CMB with the DESI BAO, there are some little shifts, but all below 2 sigma. There's nothing significant.
So I think it's almost the first slide or the second slide in your talk.
Okay.
Further. Yeah, no.
No, yeah, I'm sorry.
There you go. So
okay.
lower panel, I think the gray is Planck, right? So there's like that's the question. Do you consider that a discrepancy, or there's no discrepancy at low Z?
The answer is the answer is that as far as the implications for cosmology, I think we did look into any sign of discrepancy or something that could affect in any way the results. We did dig into it, and we did look into it, and we did look into this. And as far as the cosmology results, nothing is affected.
But that's why we have a preference for a slightly different lambda CDM model than the best fit Planck lambda CDM model. You're right.
Yeah, it's a slight, so we see that there are some slight differences again, but again below the 2 sigma.
Yeah, thank you for that very nice talk.
Thank you.
So compared to the SDSS data, which has very similar constraining power as the DESI year 1. In the DESI case, you see this preference for a non-standard WA, W0 result. Do you have a sense of whether that change is driven by the DESI year one data or a combination of the updated CMB data and also supernovae data you're using?
Good question. We did check that. It is driven by DESI. And also, let's keep in mind that DESI is fully blinded, as my colleague said earlier. So it's a fully blinded analysis. And no, the results are really driven by DESI.
Great.
Good
Then my
question.
follow-up question is, do you understand what changed between the SDSS set versus the year one set that caused that change? Is that the high redshift result? So that will depend very much on the Lyman alpha BAO measurement.
It's a good question. I think you should have asked your question when my colleagues were there up, so they can answer.
It might be a
I can give it. I can take a crack at it. So I think the all I can say is, and one of my colleagues about this could add, but certainly. Certainly, I think what have changed. So there is the blinding analysis, and also what has changed is there are again some small changes here and there, and some small changes in there for the Lyman alpha or so forth. But again going back to there, as far as cosmology is concerned, it is not having any effect. And say again your question again, just the last part about the Lyman alpha. So
Well, because in previous SDSS BAO results, there's slight tension discrepancy between the Lyman alpha BAO versus the rest, the galaxy.
I see your question.
So I'm wondering if in the new DESI data, how much of that has shifted and what caused the change, and whether the result that we are seeing here could be driven by that change.
Yeah, that's a good question. Should be directed to my previous colleagues. Go ahead.
Can I answer that real quick?
Yeah, sure.
Okay, so lots of different angles to your question. Totally excellent question. First of all, the SDSS Lyman alpha forest data, when you look at the whole sample holistically, everything's scattered about lambda CM as expected. So that actually wasn't really an outlier. It was something like 1.5 sigma, but with a sample size of 7 measurements, you expect that. In terms of DESI versus SDSS, there is a stronger preference away from lambda CDM with the DESI data when combined with CMB. However, when we did the final BOS-EBOS cosmology analysis, we actually saw the same preference, but it was only at the 1.92 sigma level, and that was not enough to be really interesting. And if you also look in more detail at this, right, when we combine with Pantheon, we're at 2.5 sigma. It's actually not that different. And you also see that the lambda CDM model, BOS, EBOS, DESI, consistent. DESI is about 20% better precision aggregate over those previous measurements, and we do that in a year now. So it's really more powerful, it'll become more powerful, but overall you're just kind of seeing this general trend to measurements in that, as Mustapha said, that lower right-hand quadrant.
Yeah.
Thank you.
Okay.
And it's interesting just to add even more. We see it with DESI alone, we see it with Planck slightly, and we see it on the supernova results. So combining all 3 samples, which are independently hinting at the same evolution away from lambda CDM, this is becoming quite interesting. And fortunately for DESI, this is just the first-year data. We already have the 3-year data set collected. And we haven't started analyzing it, but that will happen soon. And so we'll have much more powerful data in the very near future to see how that trend evolves. Another question? Oh, maybe here first. Yes, please go ahead.
Thank you for the talk. It was wonderful. My question has to do with the neutrino sum constraint.
Okay.
And if you checked, I mean, I'm sure that in the paper you do, but how does that compare with the global fit from particle physics? You know, and like other measurements of this?
Okay, the question, if I understand this, is we compared with other measurements from like neutrino oscillation, terrestrial experiments. What we did, okay, yes, good question. So we took, I showed only the results for neutrinos when we assume we take a prior, like the sum of the masses is greater than 0, like done in cosmology in all the previous papers. But also we looked into physical priors. So yes, we considered these neutrino terrestrial experiments, and we took the priors for the normal ordering and the inverted ordering, and we put those priors, and we calculated the bound on the sum of the masses, and we found that it is prior dependent. So it's not news, it is prior dependent, and that's why I added in the slide there. But the answer also is that our results don't show any preference for normal hierarchy, normal ordering, or inverted hierarchy, inverted ordering. It doesn't show any preference, significant preference.
Yeah, it's only a 2 sigma difference between the two orderings. If you add the prior of having sigma positive or some of the neutron masses above 0, some of the neutron masses above 60 millielectron volts. It's only 2 sigma preference for the normal ordering. And that really, as Mustapha said, the bounds really loosen quite significantly if you start allowing for a more complex evolution of the background evolution, and so allowing for W0 WA to be different from lambda CDM result, then loosen the bounds quite significantly. And I think that if that indication persists, then we do have to take that into account when constraining neutrino masses. Yes, please go ahead.
Still on neutrinos, were you able to constrain an effective? And related to that, is such constraint, does it really depend on this W0 WA model, like depending on the cosmology you consider?
Good question. I have a slide for that. The question is about N effective. So I'm gonna
yeah, I can maybe go faster here. Yes. Go ahead. That seems to work.
Let me do some practice for my clicking. Okay, here we go. So, so you see that here are the results for N effective. And all right, so here is our N effective, and then this result here is when the yeah, sure, thank you. So here we go. So we have N effective here. If you go down this result, this is the bound, this is the constraint we obtained from DESI plus the CMB, and this is the constraint in this model. Now, if I'm recalling, so you wanted to know what happens in the WAW-CDM, this here, so this is with DESI plus CMB, so we
below one.
Oh, there you go, thank you. So if we go here, we see that this bound here, the uncertainty goes to this one here. So it's practically, you see the uncertainty here is 0.17, 0.17. So as far as the uncertainty, if I'm seeing very well, it doesn't change, but the central value shifts a little bit. Okay, good question, yeah.
Yes.
Hi, thank you for a nice talk. I was wondering what happened with the Hubble tension on this W0 WA model now, because you are seeing a statistical preference for that, right? So what happened now with the Hubble tension?
That's a good one. Again, you definitely wanting to make me practice this. Okay, so are we here in, yes. So your question is about H0 and the 2. I think, yes, I can't see the top of my slide here. Where is the?
No, but well, H0.
Oh, there it is. It's the first one, yes. Okay, so your question is, let's have a look. First of all, so here we go. This is flat lambda CDM and DESI plus BBN. And here is our friend H0, right there. And then you asked me, if we go to W0 WA CDM, and we take again DESI plus CMB, it's right here, or you said DESI plus BBN. We don't have here DESI plus BBN, probably was not good enough. DESI plus BBN plus theta star, the angle sustained by the horizon to the surface of last scattering. So here you go. So you see that there are the sigmas that we obtain, okay? This is 2.3 not the sigmas, but the plus or minus 2.3. So it does get diluted. The 1% we get in the lambda CDM gets diluted. Good question.
Okay, thank you.
Sure.
Yes, Lloyd.
I was wondering if you also have in a backup slide a figure where you show these, distance redshift plots together with the model in there that's your W0, WA, best fit.
It's in the paper and not in my slides. Maybe if there is one single...
had it, I think.
No, he's talking about the blue, the
H naught?
Yeah,
you wanted the evolution of H as a function of redshift? Because otherwise the best fit, we have it on Hee-Jong's slides. I think her second slide or third slide was showing the press release Hubble diagram, where you have the ratio dV over RD divided by the lambda CDM best fit, and you had the dashed curve, which actually was going much better through the first redshift bins. It's where you see the dV of RD points that are below the unity, and the dashed curve which goes through those points is actually corresponding to the W naught double A CDM best fit DESI model. And that's in the press release, so that's available now already. Other questions for Mustapha? Yes, please.
There you go.
Hi, thanks for the talk. I'm new to this field, so maybe the question may sound naive, but I couldn't really appreciate what was the feature in the DESI data that allowed you to make this claim about the evolving dark matter. So what's new in the DESI data that wasn't seen before? So what's the new feature that allows you to tell this?
I think it's the whole data itself. It's the best fit to the data. We take the data, and blinding is very important. And if we take the unblinding and we get and we do the fit, and that's what the data is saying. So in the paper we go in a little bit, some maybe trying to dig a little bit farther into this, but I think the overall fit is what is giving us a constraint for the W naught WA. It's really a feature of the DESI data altogether.
Thanks.
Yeah, sure.
Yes, please.
One more. Hi, thanks for the fantastic talk.
Thank you.
And I just want to touch on the Hubble tension part again.
Okay.
And would you say that the WCDM model that you say, like the evolving equation of states, would kind of mitigate the Hubble tension, maybe? Because now it's evolving, so maybe you could have something that could constrain both the early observations with the late observations.
All right, excellent question. So you are telling me, yeah, we have seen this debate, this discussion ongoing on the archive, on the papers. Yeah, so there was, if we can use dark energy to kind of resolve the Hubble tension, up to the point, I think, it was shown that just dark energy itself needs these models, this kind of special models about that could an equation of state that could resolve the Hubble tension. So and then there was also the introduction of the early dark energy, but I'm not talking about that. We're talking about just the dark energy. So there is a few papers from in the field that, yes, using W, trying to reconcile to solve the Hubble tension. Maybe with this we can have a second look at that.
Can I add I'll just say also in the paper you have a plot where we show the evolution of the tension as we allow for more freedom on the dark energy properties. And you see that basically the central value of H0 doesn't change much. The uncertainties, of course, increase on our determination of H0. So you reduce the tension, but you reduce it by enlarging the uncertainties, not by changing the central value of H0.
Are you referring to this plot?
Yes, exactly. Yeah, thank you.
Okay. Yeah, I think, yeah, Nathalie is right. So, yeah, you can.
So you don't have here the central value, which is in the table. So the central value basically doesn't shift, but you see that you reduce a little bit the tension by enlarging the uncertainties. But the tension is still there. You do not resolve it, at least not with these first data.
Yeah, I see.
Yeah.
Oh, thank you.
Any other questions for Mustapha, for any of the speakers of this morning?
All right. Okay. If you want to blame something, blame it on the clicker is not fast enough. This is to go back. Okay, yeah. All right. Oh. Okay. Yeah, Rocky just took a picture.
Okay.
Oh, good.
No other question? Then let's thank all the speakers of this morning again.